Welcome to today's Wolfram Institute live stream. Today we're going to review progress made on the hypergraph, or the InfraGeometry Paclet, and the Paclet used for discrete geometries, specifically simplicial complexes and things of that nature. So, Nik, go ahead.
Yeah, hypergraphs, simplicial sets, whatever. It's just like the whole idea of creating this new Paclet is that we have a lot of notions of doing geometry on discrete combinatorial objects, right? We had some, we already had a hypergraph Paclet. Maybe we can also review that a little bit. But we don't know how in general we can do some topology and geometry of hypergraphs, because usually people talk about more constraint objects. Like there's some simplicial closure and all the degeneracy are lost from the hypergraph general case. And on those objects, people know how to do topology and geometry more or less. And that's the idea for this Paclet, is just combine all of these notions together so that we at least have definitions of the and a working code, right? And the idea, I guess, today is just to go through whatever we already combined in this Paclet, what kind of definitions we have, right? Maybe do some refinement of those if some questions gonna come up, maybe renaming or maybe some change the actual definitions, whatever goes. Right? Maybe I have some examples already, but I guess maybe we should just go through basic stuff. Like here's the guide. We haven't published this into repository yet, but we at least have this guide. That's the only documentation that we have for all the functions that we currently wrote. And maybe like a bunch of usage messages, just like and just LLM them together. So for now, but yeah. So what should we start from? So I think the basic idea is to have a complex. It's almost like a hypergraph. Maybe we just actually review what we already have in terms of hypergraphs, because it's supposed to be a representation of most general kind of object like this, right? So this is supposed to represent like a face, a triangle, but right? If you add some two-dimensional edges, it's like in a graph, it's a one-dimensional object, or you even have one-dimensional objects which you already have, like these vertices, but in hypergraph you can have them explicitly, like that, like this, or maybe floating around. Also, in hypergraph, it's so general that you can even have like an empty things, like an empty edge is also allowed, right? But it's like if you, without any additional structure, it's really hard to do something useful if you have a large hypergraph. How do you define topology and open sets and geodesics and curvature and things like that on the hypergraph? So that's why we have an idea of a complex. Complex is basically, we should think of it as a closed hypergraph. So if your hypergraph is this lists of edges, then when you close it, it will get rid of these empty edges, and it will also close all the triangles with the boundary edges and all the boundary edges and the edges with the vertices like that. So if you turn it back into hypergraph, it will keep it will add this additional structure. So in a way, now it contains all the boundary explicit. So that's the complex, right? So and we have like, this is the closure. The index hypergraph is just an index complex are some convenient utilities if you have like a hypergraph maybe expressed in terms of some symbols, I don't know, or strings or whatnot. If you index them, do the index hypergraph, an index complex, it just renames them with integers. So it's analogous of index graph in the system, right? The same goes for the index complex, it just adds the closure to that, right? So what else? By the way, you should like interrupt me if you like some questions arise or maybe more.
Yeah, so one question is,
Functionality.
with hypergraphs, you can include the same vertex multiple times within a single edge.
Yeah,
Is
you
that
can.
does that make sense for complexes?
Yeah, for hypergraph, you can like put a bunch of same. You have the idea of degenerate edges and also degenerate vertices. There are like two types of multiplicity you can allow in the hypergraph. Like you can repeat this edge twice, right? It's allowed. Or you can even repeat same vertex within each hyperedge more than once, right? You have some kind of loops now. So that's why there are two notions. If you have loops like this, so a single vertex repeated more than once in a single edge, that sort of represents a degeneracy. So we usually call it degenerate edge, or something like that. And if you have multiple edges, completely the same edges, that's like a multiplicity. So this is two properties that the hypergraph can constrain and to get the simplex. Simplex does not allow that. The abstract simplicial complex does not allow none of those. Like
Yes.
neither degenerate or multiple edges. Right.
So
But there is other objects. Yeah, go ahead, Pavel.
this is maybe something what I'm trying to kind of extend now. The claim would be that if something like this happens, that if you have, for instance, this degeneracy of the set of edges, then you would obtain delta complex. If you have also degeneracy in each edge, then you would obtain basically simplicial set because you would have to keep track kind of degenerate faces. So
Yeah.
maybe the claim would be that you can close these more general, that the non-simple hypergraphs close into not into delta complexes or simplicial sets in the most general degenerate case.
Yeah. I actually had like this table made a while ago, trying to list all the possible things. Like maybe I should just put it in the notebook here. So this is like at least if you want this representation as a incidence list of lists as your representation of all these combinatorial objects, then you have like at least these four properties that you care about, right? And you just can turn them on and turn them off, and to get different things. Like half of those are some different kind of hypergraphs because they're not closed, right? They allow like arbitrary, like you don't require every triangle, every face have a boundary edge, right? It's not required for the hypergraph. That's what closure means, right? So if you're not closed, you can get like simple hypergraphs, multi-hypergraphs. Multi means basically this multiplicity of edges. Oriented, if you are allowed to sort them or not, right? Simple are those, either they have loops or not, degeneracy of vertices. So basically half of them is just differently prefixed hypergraphs, right? But when you allow closure, you get all these abstract simplicial complexes and delta sets. They only differ in whether you allow the degeneracy in the vertices and things like that, right? There's some unclear things whether this is like another type of complex or not. I'm still not sure. But yeah, that's the table. And the idea, I guess, for this Paclet is to support all of those, and on top of that, also more general things like even these CW complexes. I guess it's just we have to generalize it further to not just have this list of lists, but maybe some matrix that represents how the things glued together, right? Well,
you can always get from any of these more general definitions, you can always get kind of, but it's a kind of a wrong way procedure, because you can always kind of take the union, right? You have a list that you take union, you get a set. You have a list of edges, you take union, you get a set. So you can always get abstract simplicial complex, but it might not. You lose some information. Maybe the hypergraph had information of a different geometry, and by doing this, in case of these degeneracies, you are maybe getting different some different geometry than the hypergraph actually originally was supposed to represent. This is kind of, I would think about it maybe like that. And if you want to represent, if you want to keep what the hypergraph wanted to represent, you would need to really take more general object like the simplex delta complex or simplicial set.
Yeah, right. So I guess we have a bunch of terminology. Like a simplex dimension, we just call it's a length of this sublist, one less of that length, right? So that it makes sense that the vertex which contains a single element is of dimension 0, so it's like a point. So this makes sense. Cardinality is just the number of those. So if you have like an arbitrary simplex like that, which is a triangle, I guess, right? The simplex cardinality is plural, would be like a list of all the possible dimensional, like there are 4 zero-dimensional points, 3 one-dimensional edges, a single face. So this kind of list was also related to some topological numbers, like Betty numbers, so that you can easily compute things like early characteristic of the complex and things like that. Though it's a theorem that you can compute it with cardinalities. Usually you define it completely differently. And we have such definition like this complex Euler characteristic. If you look at the definition, it probably contains, it's kind of hard to read, but it's pretty close. Right, it just adds the sign to this. So it's something like that. So each simplex, so we call each element of that complex J a simplex, so each one can compute a weight, right? And if you add them together, you get some number. And another way of getting the same number, for example, is to get these cardinalities and make a iterated sum. You basically dot product it with something like this. That's a Poincaré theorem, something like that. Euler Poincaré theorem, basically, that you get the same number doing these completely different things. And there are other ways of doing that.
But I mean, for the triangle, that was thrown off by the inclusion of the extra vertex floating off vertex 4. But yeah, so what you're talking about is like the vertex, the number of vertices minus the number of edges plus the number of faces.
Yep.
Alternating something like that.
Yep. So the typical Euler number of vector. You can also compute it like this Betty vector that doesn't count things in the complex, but actually computes some linear algebraic property, like the kernel dimension of some particular matrix that you can construct. Let's actually try it and see whether it works, if I remember correctly. So this is some matrix, right? And it's a block diagram, so we can extract the blocks. So it has some. So there are 3 block matrices, and if you compute matrix nullity, this is also built in with some numbers, and if you sum them together, you get the same number. So this kind of theorem holds for different kind of complexes, I guess.
Yeah, what are those Hodge matrices? What is that describing?
So let's see. Yeah, there are many types of matrices that you can extract. So this is like the main tool for geometry. Is just define a bunch of like propagators or representation of the complex as a matrix, and then you can study those properties, maybe some spectral properties, its eigenvalues, to talk about its geometry and things like that. And this is just one of the matrices that are very useful, right? Maybe it's has a not very straightforward definition, but you can kind of read it.
Maybe I can comment on that. What is this
Yeah.
Hodge matrix? It's basically, so if you have like delta complex where you are having boundary operators, so an operator which is associating to a simplex, it's kind of the sum of the boundary simplices with so it associates to a simplex. It's I mean, in delta complex you have like ith boundary, right? You have for an n simplex you have 0 to n boundaries, and you have like boundary maps. First boundary map is like zeroed boundary map is associated, is giving the 0 boundary, first boundary map the second boundary, and so on. And basically in algebraic topology, you normally define this boundary operator as the alternating sum of the delta of the del I of these boundary operators. And this Hodge matrix is a transpose of this boundary operator. So it's a basically action of it represents the action of of the boundary operator on the forms on the simplex. A form on the simplex is like a vector of values. For each simplex, you have one value, and if you multiply with this Hodge matrix, you are getting, like, from the mathematical viewpoint, you are getting like the form precomposed with the boundary operator. So it's just like
Right.
transpose
So
of the boundary.
I mean, it looked like the first matrix was a vertex adjacency matrix,
Perhaps.
where like the vertex is connected to another vertex if there's a one-dimensional edge connecting those two zero-dimensional points. But
Wait, sorry. So this might be the matrix of the Hodge Laplacian. So you take like d plus d plus d star, and you square it, right? Yes, this is precisely what he's writing there. You square it and you obtain the Laplacian. Yes, and where d is the one which I just described. So d is the transpose of the boundary operator, and you sum it up with the transpose, square it, the sum, and obtain the Laplacian.
Yeah, basically it's like there are many definitions, all of them associated to at least three people, like Dirac, Hodge, Laplacian, right? There are three people involved, and you have a bunch of definitions. There are some slight confusion how to name each of those. So it's like this Dirac block matrix. I think I just invented it because it made sense to name it this way, right? But I haven't seen it like named this way. It's like they're all called Dirac matrices, right? And and we can't just call everything Dirac matrix. We have to like add something like Hodge, block, connection. That's why there are many of those, right? When you actually make them into some code like this. So yeah, but yeah, I think what Pavel called a boundary. This is this D transpose operator D. It's one of them is differential, another one is boundary. They just transpose of each other. In terms of graphs, they are just incidence matrices. They tell you about how vertices are connected to edges and edges connected to vertices. So it's in a way, if you go from vertex to an edge, it's like a differential. If you go from an edge to a vertex, it's like a boundary. And if you generalize it to faces, when your faces have an edge and edges go to faces, it's like a differential, and obviously edges are boundary of faces, things like that. And that's why you have block matrices, because you have from vertex to edge, from edge to face, and so on, for arbitrary dimensional simplices. And you can define things like that.
Okay, so
Yeah.
it's like you have a list of different adjacency matrices.
It's more like incidence matrices. Adjacency, they are always like on the same type of dimension for columns and rows, right?
Oh, I
For
see. Yeah, so
a
like,
graph, it's like vertex versus vertex. Here, it's like a k plus versus k plus 1 or minus 1.
okay, so you have like a
Yes.
list of edges on the columns and then a list of vertices on the rows, or vice versa.
Yeah.
So you're
Right.
And you
comparing.
put and the number is plus minus one is the boundary orientation. So if the permutation which writes the bigger simplex as like the one which you are omitting, and the rest, if it's like odd, then you get minus one. If it's even, then you get plus one.
Yeah. It's more like a signed incidence. Like, for example, built-in system function for graphs. Works like a boundary, right? It tells which vertices are the boundary of each edge. But it doesn't it actually is signed, right? It depends which one is if your edge is directed, it knows which vertex is source and which one is target, and that's where the sign is coming from. So this is basically, and if you generalize it to faces, you can do essentially the same thing. It's just for faces you don't have source and target, you have some permutation of it's an odd even permutation of vertices. That's
Right.
how we decide on the
Yeah,
side.
phase has like a
on the
cyclic
side.
orientation to its vertices or some sort of order, and
Yeah.
similar notions for larger dimension of simplex.
Mm-hmm. Okay, and I think like this complex incidence matrix exactly does something like that. Very similar. Maybe it's by default, it's like take some dimension or something, I don't remember. I think 0 means between vertices and edges, right? So it's like k versus k plus 1. So there are 4 vertices, 3 edges, right? If it's 1, this is a single face, 3 vertices. So we get all these different blocks. Yeah, I guess we need some. It's kind of boring without visualization. I should have. At least we have at least one way to visualize those complexes in general, because they're very abstract. They don't have any coordinate information in them. We have to create a way to embed them in some space, so that it, like, the triangles looks like triangles, and tetrahedra look like tetrahedra. So we have like simple embedding function that turns it into a mesh, tries to preserve it. Let's do some more complicated example, I guess. We just close this one. So if this is the single triangle, this is a tetrahedron. It's so small. Right. If you add a face to it, like to something else, so we have an edge, and make it a face. So it's like some particular embedding that tries to make all these simplices, triangles, and tetrahedrons so that they not overlap and they still look regular. So that's why we can't reuse our hypergraph, even though it's nice. We even have a 3D version. You can make this.
I like
It's
that.
a little bit confusing because it's like triangles are stretched and doesn't look like tetrahedron. This is more obvious that it represents a simplex, right?
Mhm.
This is one simplex, this is another simplex. We just add some other one, like 2, 3, 5, like this. Okay. So that's how you can turn them into a mesh regions. And then you can use all the built-in region functionality to work on them. The embedding is like just a little bit slow, but yeah.
Yeah, which embedding is this? Is this Spring Electrical?
It's a custom one because we can't use the graph embedding because it doesn't know anything about faces, but we have to make some repelling force between faces so that they not overlap. Because if you just try to embed vertices and edges, you can have a edge between an edge and another edge goes through that triangle, right? And we don't want that. So we want some additional force so that this doesn't happen. So it's like if you're interested, we have like this. I wrote this algorithm here somewhere, like this complex embedding. Right, so it's very slow right now, but this is some repulsion force, some energy definition. This is like works between every pair of simplices. So this is like all the subsets. So that's why there are a lot of terms. So it's not very efficient, even though I compile it. It still can be slow for sufficiently large complex. Like if you add more, let's do some, add more another tetrahedron or something. Should have, yeah.
Oh, I see.
We
You have
still
that
get this
collision.
scheme, but it's sometimes they're impossible. I think it's like if you, I don't know whether you can actually embed this without overlapping. Well, you can if you allow for non-regular like hypergraph things. So maybe that function needs some other energy definition. Like hypergraph 3D gonna be what? It's gonna be. It also overlaps them, right? No, it's harder to tell. Another reason why we need this.
Well, that's an interesting optimization problem. But yeah, I can see why in a lot of cases it's impossible.
Yeah, if you allow some kind of stretching, then it should be possible. But yeah, we have to get some. We should allow that. It's just with some coefficient, maybe, I don't know. But that's a good problem to solve. Okay. So what else we have? So we have So we know we have these complexes just represented as a list of simplices, right? A bunch of functionality. The topology related functions, right? For example, if you have the complex like that, in a way, this definition of a star of a simplex, which is basically you take this and map this. In a way, this represents the topology of that complex. It's a list of open sets. So each of those elements now is a star, which is you can think of it as an open set. So that's would be called a topology of that complex, right? And there are, of course, some mathematical definitions that go into that, so that you can maybe.
So what are we looking at here? Starting with the first vertex, and then
it's like a neighborhood. So
all the simplices
you should
in
read
the
it as like
complex
all
that are adjacent to that vertex.
Yeah, it's all the elements that contain it. You can the simplex is contained in a given simplex, right? So you can think of it as, so it's almost like a neighborhood. So for example, like if you look, if this is our complex, if you want a neighborhood open star around this vertex, you get everything that contains it, right? Contains one, including itself. And then there's some other obvious convenient definition. I think I haven't even listed it. If you don't want the vertex to be in this list, it's called a sphere, I believe. Right? So this is like an open set, maybe a bow of sorts, and that would be a sphere if you exclude itself from that set. So that's like one of the goals of this project is like have this definition. If they're very straightforward, is just we have to name them and create those so that we can then refer to them, right? The core is the other way around. The simplex core of a particular simplex is what is contained in it. So for that face, for example, it's all everything basically. Maybe for that edge is everything that contained in it, including itself. And again, there's a simplex core sphere, which is this all the simplices. Well, in this case, you don't even have to provide the complex, because everything that contained in it you can already derive from itself, right?
I feel like
So
simplex star sphere is sort of like you have this closed sphere, and then you remove like the interior point. Then the core sphere is like an open ball. Like you're removing the top level, keeping everything inside.
the star
removing
is
the shell,
open.
I guess.
Removing it, yeah, we can also define. Do I have listed it here? I think I not listed, but this is also like simplex unit sphere. So for this particular, this is like a star. Like a star would be that edge. It's just this, but it's like everything else. But if you close it, and then complement something like itself, something like that. So that's how you can define the unit sphere. There it is, right? So that's the definition. So that maybe from that definition you can start making some topology. So this is like spheres. Around each simplex you can define a sphere.
Nik, a question: is it possible currently to visualize it in the complex mesh somehow easily? Or
Yeah, is there highlighting for these implemented?
In some sense, yes. So because we have this mesh, I think I had some convenient thing. Like if you have, let's take a more complicated one. Like here we had this one. Let's start. So we have this G. turn it once in a mesh. I think I have highlight mesh convenience. Let's see what it works. For example, let's highlight the star of that H2 or 26 or something. Is it working? Oh, we need no highlight. I think so. So
yeah,
the
so it highlighted that edge 2.6 and then the
this
triangles
space and
that
this
adjacent
space.
to it.
Yeah. This makes sense. Let's highlight something else. Maybe we don't need this. Okay, if we take this triangle 3, 5, 2, 3, 5. Oh, it has nothing.
Oh, why not?
As a star, and it just contains itself. But the highlighting works, so in a way you can inspect this objects.
Oh, there are no higher simplices which contain it. That makes sense.
Yep.
But if you did the one that includes like the things that are adjacent to it.
So like if you just pick one vertex 5 here, it's like, yeah, everything that contains it, it's all the faces here highlighted.
And you also maybe visualize the sphere so that we see what it is.
Yeah, so the simplex unit sphere around this vertex 5 would be this. So it excludes it, but it keeps these edges. So it's just like some boundary. It excludes the interior, right?
Only
This is
only
like
the red lines is the sphere.
Yeah. So this is like an open ball because it doesn't include those edges. But this is like its boundary. That's why it's like a sphere. So but it's like very abstract, but it's somewhat makes sense.
Can we test this out maybe on a grid graph, just a two-dimensional grid?
Okay, so let's try a small one, like maybe 3 by 3. We have like graph complex that would just
Well,
read
let's
this.
do like a 4x4. That way, when you take the sphere of like a point in the center, you can see the boundary, and it's not the boundary of the whole graph.
Let's see what this algorithm actually manages to optimize it embedding. See, it's kind of, yeah, it's slow.
And
Not good. Let's try 3 by 3. Oh, because it's like,
oh boy,
yeah,
okay.
it tries to, doesn't know it's a grid. So
Is there a
so
way to
tries
assign
to, like,
vertex coordinates for these graph complex?
well, it's a mesh. So if you already have a grid graph, you can forget about, like, this is, you should forget about these things you don't care about. You can turn it to the mesh, for example, like this. Oh no, not like this. How do you go back to the mesh? I don't think there's a way. The graph mesh thing.
Um,
Oh, it's
wait,
also
what are you asking?
actually. Oh, I have it. I even forgot about it. Yeah. So mesh functions. Yeah. So it's the one defined. So it turns the graph into a mesh, like a convenience function, right? So that now you know what elements are. Maybe you can even. It doesn't contain the faces, right? So it's a skeleton.
Yeah.
Maybe we need to make some nice visualization. We need like to make a version of it with faces. So basically, we can make it like take a rectangle, for example, just a rectangle, and discretize it. I think you can do it like that. It's just not that big. Max cell measure maybe. That's
Yeah.
something like that. Maybe fine. So we can have this mesh, right? So this is our grid, and we can turn it into a complex, of course. So this is all the faces, all the vertices on all the edges. And if we then, of course, we can't use highlight mesh because the embedding is slow, but we can just highlight this mesh directly. Like for now, we're just gonna work like this. So we can do with our simplex unit sphere. Let's call this G. Around some particular edge like this. Though we have to, because this returns, we can wrap everything with simplex. I think it doesn't work for, but you get the idea. Is it? Yeah. So that's a sphere. That would be, for example, the star around it. It somewhat works. That would be the core, which is itself, I think, plus the vertices. Yeah.
Is there a function to say, like, give me everything that is adjacent to it? That has overlap?
Adjacent to some simplex or what?
Yeah.
Well, that's in a way, that's what it is. No? Or what do you mean? Oh, it should return like a...
Like, those triangles are included because those triangles include that edge in them.
Yeah.
But like the triangle to the right or something is just incident upon that edge at one vertex. And so that's another like operation to think about. It's sort of everything that has incomplete adjacency, let's say. Doesn't strictly
I think we
contain
don't
it.
have it, but we should add it. I don't think we have this kind of function. But what would actually, maybe we should add one. This is a good to have like a mesh, like a guide like this. So what do we need? Like some simplex neighborhood or something. I don't know how to call it.
Yeah.
Right?
Mhm.
Yeah, it's good. Maybe with some parameter k, like all the simply this k.
Yeah, you could specify a list of dimensions or one dimension that you're looking for, or all sort of. There are different
Right.
ways to play that.
Of
Oh,
course, you can kind of do
distance
it.
away. Okay, well.
Oh, you can kind of forget about it. Like if you have this complex, you can always turn it into a graph. You just pretend that all the triangles are like clicks. So if there's a notion like of phase graph. We have a phase graph here. Yeah. So phase graph is basically turns this complex into a graph, but it makes it each triangle just becomes a click, right? And there should be graph complex should recover it. It just maybe with some renaming of variables or index complex. Maybe not quite. No, but yeah, this is like actually what we did accidentally is this barycentric refinement, because it adds additional vertices when you do it like this. If you use phase graph, but there is another thing which is more conveniently called just complex graph. Right? This is like that corresponds to this one. But the phase graph, it makes an additional vertex inside each face, right? So it refines each vertex in an additional vertex. Each triangle with an additional vertex.
Well, is it a subdivision?
It is like subdivision. It's basically
How does it
like
connect?
barycentric refinement is basically defined like this. You make a turn complex into a graph with the space graph, and then you turn it back to the complex and you can apply it again and again. For example, if you start with a simple complex like that, like just a single triangle, right? If you barycentrically refine it, you get this. Well, maybe let's start with the graph. I think it only works with graph, like a cyclic graph. Or is it cycle graph? Cycle graph, right? And just do the nest list or something. Do it like multiple times. 4. So that's what barycentric refinement is doing. So we start with this. This like the embedding is kind of weird, but it's also a triangle. If you straighten out these edges, because it just puts a vertex here and a vertex for each edge.
Oh, I
Right.
see.
And
So
then
it takes the midpoints of
Yeah.
the edges and connects those to the boundary of every edge, and then it takes the midpoint of the triangle and connects that to the midpoint of the edges.
yeah, something like that. But you can also think of it in terms of just doing this. So if you turn your complex into a graph and then you make a phase graph out of it. I think it's graph complex. I think it's equivalent, right? So graph complex of a graph is you turn each click into a particular dimensional simplex, depending on dimensionality of your click. And the phase graph, yeah, just turns every simplex into a new vertex and closes it by adjacency, something like that.
Right. You did the phase graph for that complex up above. So that's adding putting a vertex at for each face and connects those vertices. If two faces are adjacent upon an edge, their centroids are connected. Is that how it works?
Well, just see by example. I don't know. I think it's easy to see what's going. It's like, oh yeah, the labels also are helpful, right? So it just puts here an additional vertex. If you also have 1, 2, 3, so that's a new. So the face became so every simplex of this original complex, every simplex becomes a new vertex, and then you just connect whether they actually contain or is contained in it just by the subsets, right? Edges would represent whether they are subsets of each other. Mm-hmm. Yeah, I think that makes sense. All right, so we don't have a lot of binary operations yet. Because most of the time you can use some graph operations already, because you can turn them complex back and forth between the graph. So there's some notion of a graph join already built in, so we don't have to. Even though for complexes it's sometimes called completely different. But yeah, we can just reproduce all the graph operations, but do them on top of lists like that. So what else should we? What's next gonna focus on? Have like
Sorry, I have a random question.
Yeah.
Not to derail the direction right now, but have you thought about how to visualize greater than ternary edges?
To visualize. Hold on, try it again. Which edges to visualize?
Edges that have more than 3 points. More than 3
You mean
nodes.
well, you
Upper
mean the
edge. So a
triangles of? You mean
no,
like
no,
the
no, more than
face?
triangle. Yeah.
Well, in 3D you visualize it as a tetrahedron, like this green thing, right? In 4D it's gonna be problematic. Then we have to go into hypergraph visualizations like that. Here,
Yeah, that's what I was asking about. Have you got any idea of how you would do that? Like, have you got any?
well, you can do it like that at least.
Yeah. So that's
but it's kind of weird.
Well,
well,
yeah.
that's
So
assuming the node's on a plane. So, yeah.
Well,
for
we only care about
simplex,
connectivity, right?
No, but I'm saying if you were to embed this in a 3D space and those nodes happen not to be on the same plane, how would you visualize this edge? How would you bend it
Well, we don't
into
even
two
have.
dimensions?
We're dealing with abstract objects. We don't have any point coordinates of points, right?
Sure,
We
but I
only
mean,
know
let's say for example, there's multiple edges here. I mean, the point is, it just so happens that these 5 points exist on a plane, but they don't necessarily have to. If it was a more complex system where there's a whole bunch of points and you're trying to arbitrarily connect 5 points in that 3D space, then this hyper edge would have to. Okay. Interesting.
You can
So
bend
what
it
mathematical?
slightly.
Yes, okay, this is what I was asking. So what mathematical model are you using to bend the plane here, bend that hyper edge?
I think I do some. I think I sound weird. How is it called? The algorithm. It's some sort of minimization again. So you create some initial surface and then you minimize some tension between the vertices of the surface, and that's how you get it. So there's some optimization going on there.
Is it a SOAP form optimization? There's this idea called a
Yeah,
SOAP.
something similar. Yes.
Okay.
yeah. So
Basically
it's
minimizing
Okay.
tension of that surface.
it's
Very
probably
cool.
start out with
Okay.
like a fan of triangles going to all these 5 edges, and then
Yeah, there's some weird polygon.
mhm.
Mhm.
And then you subdivide that like 1 or 2 times or a couple times to get something smooth, and then you optimize that to minimize bending energy.
Oh, we can take a look at the code. Why not? I can find it's in the hypergraph Paclet though. Where is it?
Oh my goodness.
Embedding. Have some. Yeah, it's a mess. I know. Don't tell me. I'm just trying to remember. Oh, the
So you're not a
salary.
fan of adding comments to your code,
Just ask LLM these days. Who cares?
eh?
You just go. It's like you just go like this. Then, I know. Review. Maybe it's gonna fix some bugs or whatever. And ask questions. Whatever. I'm gonna do it right now. But this is all the algorithm. I think this is like the function that the tension. That's how it's called. Laplace Beltrami.
Sorry, how do you say it? Laplace
Beltrami.
Beltrami. Interesting.
Yeah,
Okay.
I don't think I haven't even wrote it myself. Maybe slightly modified it, but I just found it online somewhere. It's a common algorithm to do. Yeah, just takes a mesh, number of steps, and it does some refinement of that mesh.
So you flatten it with the Laplacian combinatorics basis.
There's some linear. linear system has been. So whatever, I don't quite remember how it works, but yeah. So
So you're
anyone
using like gradient descent, or you're using like gradient descent to get to the lowest energy or something.
something like it should be, yeah, because it steps. It's so it's not like a gradient. It's an exact gradient because we're solving linear system. We don't have to do some completely numerical thing. So we have an exact solution at each step, but we need to do it multiple times, something like that.
Right, I guess it's like, you could have this mesh and it could be the vertices are scattered. You treat each edge as like a spring that tries to like pull everything tight, and then the mesh will sort of come to an equilibrium in a kind of a nice way.
Yeah.
It's probably akin to like a mesh. A cloth simulation for 3D graphics.
Which simulation? The
A cloth simulation.
cloth?
Yeah.
Oh yeah.
Yeah, I don't know. I'm not sure. I don't think cloth is exactly right. When I looked at 3D graphic stuff, there was this concept called soap form. They use it in architecture as well when they design certain like structures for physical buildings. They use that specific energy minimization called soap form. Who wrote the code just above that section that you're looking at with the comments in it? That doesn't look like your style, Nick.
Yeah, that's why maybe I
What's the
took
blame
this
on
part
that?
from somewhere. Yep.
Oh,
It's
so
kind of
you have to get blamed, but it's not your code. Okay.
Yeah.
Okay, cool. That was my question. Thanks.
Okay.
There could be some natural. Just the last thing we were talking about was the product. You can also define immediately some Cartesian product that you would. It's very simple. That you would take. You would basically take all the tuples of the simplices, right? I mean, you would have to rename the vertices in the second list, in the second simplex by some unique symbols. Then you would take the list of all tuples, and for each tuple you would join it into a simplex.
Well, that's what kind of this thing is doing, I think.
Is this what complex join is doing?
Well, it does some renaming, definitely. Like if you have this single line, right? Have this line, and you join it with another line. See, it's like that's the subscripts. I think that's because it has to. That's the way it refers to the original. It's like whether this vertex from the first complex or from the second, right? But what is actually it represents now is this. I mean, it maybe doesn't work. Did this works? Can I fix it or not? Yeah. So if you join two lines together, you get a tetrahedron.
But in this I would imagine something that the vertices would be like pairs of vertices. This would be this. Maybe this join is another operation. You have a list.
This join operation, it's like it's taking two separate edges, and then also adding in like connective simplices to join them together.
Yes, this is
okay.
It seems like that he is taking one simplex, another simplex, and then he is adding, one complex, another complex, and then he is adding joints, all possible joints between the other simplices.
Okay.
And this is not Cartesian product. I think there can be also Cartesian product, which is taking as vertices the like pairs of vertices of the original, right? So you have and then as simplices are going to be all the tuples unioned.
Right. So this would be different from union operation, this join operation, and then Cartesian product. For instance, like I want to think about taking a line segment and then a triangle and seeing if that would make a triangular prism as a Cartesian product. Like that.
Yeah.
And
for
I guess would those be completely disjoint, or would the triangle have to be incident on that edge at a vertex?
That's right. So now we're basically talking about all the different graph operations like this, right? Because we can do all the things on graphs. So if you want the product of the of a triangle with a triangle, Cartesian product would get this, right? If you turned it back into the complex.
what is, by the way, index complex doing? You are all the time using it. It's just re-indexing by one to
It
one.
renames it, yes.
Okay.
It renames the vertices because there's some weird overlapping again. Here I think we can easily avoid it, so that's
Now
good.
make the second one a line instead of a triangle.
Yeah. It's a weird embedding, but it's basically like just
Now, does it
it's
change
like
if it's like 1, 2, 3
rolling.
for the first one and then 4, 5 for the next?
Because the graph product is turned into this, right? This kind of makes sense. If you have a triangle and an edge, that's what Cartesian product would do. You can try all the different products that you can do. Normal, lexicographical. It's the same thing, I think. Just normal. Again, not very different in this case. Rooted should be different. It's weird. Then the tensor product.
Tensor prod. What does that do?
Let's see what it does for the complex.
Got rid of the triangle.
Got rid of the triangles. Yeah. So there's no clicks here anymore. Why is it not a click?
Yeah, going back to James's question. So before we had like these two pentagonal faces. Like those pentagons were rendered as like these curved objects in 3 dimensions. That was an optimization problem.
Yeah.
But so like related to that, it's like when you in a simplicial complex, if you have a simplex with 5 vertices in it, that's going to be interpreted as a pentatope, as a 4-dimensional polytope. And so you can't overwrite the dimensionality. So like 4 vertices, it's going to be a tetrahedron. It's going to be the 3-dimensional simplex. It's not going to be a flat square, for instance.
Yeah.
Okay. So
that
a flat square would be triangulated into 2 triangles adjacent on the diagonal edge, let's say.
What? Hold on. What?
To describe a simplicial complex of a square, you first have to take the.
Just 2 triangles.
Yeah, it'd be the union of 2 connected triangles.
Yeah, we always assume triangularized meshes in a way. So we need to because it's a simplicial complex, we need to decompose it into simplices. So we only have simplices which are points, edges, triangles, tetrahedron. How did you call the high dimensional tetrahedron?
Pentatope.
It's in the when you have 5 vertices.
Yeah. 5 vertices make a
And then
4-dimensional pentatope.
Heptatope or something. What's next? All right. So what else do we have? I don't want to go like into all the weird curvature computations, things like that.
Well, I mean, have you made any headway with curvature? Because that's something I've been thinking about a lot. To measure.
I've defined a bunch of them. Because I found a bunch of definitions. This is the classical one for graphs, I think. So it's not interesting. I haven't even written it myself. I think it's just LLM wrote
Wolfram
it.
Ricci curvature for graphs.
Because it's like a lot of...
There's a curvature defined for graphs already by Ricci or Foreman.
I think so. Like this Foreman Ricci, I think it's the first thing you find for the curvature on graphs, something like that, in the literature. So I haven't looked into it myself too much, just define it. But I have like very specific to complexes like this curvature and this curvature. I think I have another one that I haven't put in the guide. I forgot how I named it. How it wasn't called. This Lifshitz curvature, which is like defined on some averaging across graph automorphisms, which is a bit weird. This is usually some polynomial. There's another one. Of a sectional curvature also on graphs.
Yeah, but that would that depend on the embedding and a spatial embedding?
No, it's a kind of some weird. I think it can also be defined to complexes, but it defines for the stars and neighborhoods, so it's not embedding dependent. But I don't like understand it very much right now. It's some kind of averaging. It's like spreading all the and like the weight of the vertex into its neighborhood vertices, something like that. That's why there's some division by 3 in there, because it's a face.
Is it an Oliver Nils definition?
Yeah. Yeah.
Only there, or is it something more known?
Maybe because most of this definition is just Oliver Nils, right? Some refactoring of his definition packages in the app, trying to understand them. I think like many of them are pretty novel, so pretty hard to find them in other sources. Yeah. I don't know. What else do we have? Of course, we want to include some topological data analysis into the Paclet. This would involve another types of complexes than when you have points and you can build on top of coordinates some complex and talk about topology of some arbitrary point set. This is like the Vietoris-Rips complex, which is constructs from data. That's what it's somewhat helpful and useful in data science if you just have some points around and you can use topology to describe and some properties of that. Yeah, the
Right, I guess.
the term you need to know there.
You have all these points, you have all these
persistent
connections between them, and then do loops exist in that space or not? That'd be one question.
Yeah, as much as I understand it, usually it's like done like with this persistent homology tool. It's like if you have some data set, maybe it's dimensionally reduced or something, you just have a list of points, it's representing some features of your data, and then you try to build some balls around it with a ever increasing radius. And look at how your topology changes, like some Betty numbers, right? And at some point when it stopped changing, this would represent some very useful feature, and you keep and this particular radius is useful to somehow describe your data, right? Something like that. Or
Yeah. Like if you start on a cylinder and just make a patch growing from one of the points eventually that patch will like meet around the other side and like intersect with itself.
Right. Yeah,
And
certain
so
intersections.
yeah,
Like
you
as soon
get
as
like loops in that topology eventually.
so in a way, that's a useful tool, but it's like I don't think it has a lot of successes in the actual. It's maybe just few of them. It's cool to
Have you
use
looked at
topology.
like Hausdorff dimension for graphs?
I think like what Oliver Neal's one of the main points he making is that the graphs and complexes are not Hausdorff. They're natural combinatorial that are not Hausdorff at all, and that it doesn't make sense to even use Hausdorff topology on them. So it's not Hausdorff a priori, because the like this construction that we just did with open balls, unit spheres around some simplices. They how does it? They never. Well, basically, you can't really make them not intersect or something like that. Neighborhood vertex is always going to have an intersecting open sphere, right? In the continuous space, you always can decrease the radius as much as you want so that your open sets stop intersecting, right? But here you don't have it, and therefore these objects are not Hausdorff. They have Alexander topology. That's like the
So
name.
yeah, Hausdorff is sort of like a infimum or some sort of limit of the neighborhoods that like all the sets of neighborhoods that like cover the space. Yeah, it's usually Hausdorff. I guess yeah, you're right. So it's usually in the context of like Euclidean geometry, or some sort of manifold.
Yeah, I forgot like the right argument, but yeah, the main point is that it's not Hausdorff, it's Alexander topology. It's like a completely different thing, in some sense, but perhaps more useful for the discrete combinatorial objects that we do.
But like yeah, I mean, given an arbitrary graph, like a normal graph, it's like, how do you tell what dimensionality that graph might be?
Dimension, yeah. Well, for dimensionality, we'd also have some different. We have different ways of defining computing dimensionality for graphs. Like in the physics project, we have some notions of dimensionality using some growing balls of the graph distance radius, right? But it's kind of when you assume some distance, even in terms of graph distance, in a way you're doing some geometry, right, with that given metric. But there's some notion of dimensionality, like this inductive dimension thing. This is like some weird definition that I also need to understand better.
Actually,
But
can we get in?
It's
Can
like a
we maybe-
topological dimension. Yeah.
Can you maybe try to get into it? Try to compute something, some examples of that, and to understand it, what it actually does, this inductive dimension.
That's right. I think it's not even local. I think that's see it's a like how it is defined. It's computing all the spheres around all the vertices. And you assume that the dimension of the empty set is -1, which is kind of weird, but yes. And then you average things out. All these complex dimensions, that's for all the vertices. Yeah, let's try like this mesh, this graph thing. Let's try to see what it actually does. So it's 2. Okay, it makes sense. So at each vertex, this inductive dimension says that it's 2. Right? Let's try like whether it actually makes any sense. Let's try the 3D mesh. What is gonna do? Can it curious? How do we do? Can
Might
do
just be
the
like
cube?
looking at each vertex and then adding up the recording the maximum. Okay, you look at like a vertex neighborhood. Okay, put it to one of those other graphs that was like you had a tetrahedron with like a triangle coming off of it.
Yeah. Where's this? Like this one?
Yeah.
Can you maybe make it so that we see the definition, the definition in the code, so that we can kind of? I still don't remember the definition.
Yeah. Let's just
If you copy it somewhere.
I'm just gonna put it here. Okay. I'm gonna make it larger, by the way. Should have done it long time. Well, this one is still kind of small. Okay.
There we go. Thank
Okay.
Thank you.
So, all right.
Oh.
Okay, let's do it.
Okay, so maybe it takes like the average of all the adjacent simplices.
Yeah.
Some function of that.
What will it do if you have like curled up dimensions? Because you could define a graph that has curled up dimensions, and then at first it looks like it's, for example, 3D, and then if you go further, if you, let's say, you grow a ball, it will grow like as if it's in 3D, and then if you grow it even more, where the ball is larger than the curled up dimension, and it becomes only 2D, for example, right? So then what would the output be of this definition?
Well, we just have like you get a local dimension, right, at each vertex.
Oh, okay.
So you get different numbers. Some of them are like closer to 4. So, like if you just have if you close your five-dimensional simplex, it's gonna have like 4-dimension around each of the 5 vertices.
Oh, okay.
If you attach some tetrahedron to it, maybe it's with an additional vertex. There's something closer to 3, right? Something in between.
Okay, nice.
Okay, and it's defined like this, so it's in a way it's more direct than computing some graph distance. But because you're basically using spheres, in some sense it's very similar. Maybe doing exactly the same thing, but at least defined using these notions that have topological meaning. All right, so this is the dimension. So what else we have? Okay. Should we look at the curvature, trying to understand what the hell is doing? I can do the same thing for curvature. Not the polynomial. Well, in terms of polynomials, I guess it's a bit weird. There's even the definition of torsion. I just haven't included it yet. But you can even compute very topological notion of torsion for this object. It's related to some superdeterminant of the matrices that we can compute. Those Dirac matrices, you can compute some superdeterminant, basically iterating sign for each block and multiply them. Yeah. Oh, JD6. JD6 are kind of. I just coded them yesterday. They may be interesting. It's like some general notion. I have some examples, by the way.
Yeah, I was looking at what Oliver Knill, one of his videos where he had this discrete structure and a propagating pair of triangles that like were flowing on it or some sort of trail. So it's like to follow geodesic, you have to be some sort of object and then have some sort of orientation of direction of motion, and then you just kind of like some way to follow the geometry along that direction to make a path.
This is what kind of example I was looking at. So anyway, how many of those? This kind of code enumerates all possible JD6. It's like they're not supposed to be intersecting even. So if you have this particular polyhedron.
Mhm.
This is all possible geodesics that you can have.
Is that starting from a particular triangle?
Yeah, so in a way it's a orientation dependent. So you assume that there's some ordering, and that's somehow defines to which triangle jump next, right? And then you continue until you make a cycle or something. And you can even prove something that you.
Okay. Can you make this into a manipulate where you change which geodesic you're looking at?
Yeah, I was going to do something like that. Maybe like also, can I do if this is our, is there some kind of mesh union, region union? One of, so it covers everything, okay. But I want to highlight them different colors.
No, they'll be
So
too
maybe
messy. Just
we'll just do style random color something. Like maybe with some opacity or something. So otherwise they, oh my gosh. Let's do some sample as I had before. 24 GD6 maybe too much. It's 5.
it's too much. Just go back to the red one. Don't. Okay, make that like that list of red ones. So not highlight. Okay, there we go. All right, and then so
Are they repeating? Hold on. Do we have
you're
like
mapping that
repeat?
highlight function. I'll just type it. Hold on.
Or maybe, yeah, there may be just 12 of them.
Okay, now let's animate that. Okay, it's possible to look at the other side, like which triangle is being starting out. Oh, okay, yes.
It's like sometimes it involves the same triangle, but goes into other direction, right? And then how many faces? Oh, maybe I'm wrong. How many faces this has? The mesh cell count 2.
Do you understand, Nick, what's kind of the defining property of a geodesic? Why is it triangles and so on, or this is not yet understood from the paper?
Well, it's starting from the facet. The facet is the maximum dimensional simplex, right? So it's in a way, but you can start from the arbitrary one. Here, I'm computing them for faces. Actually, let's do the same for edges. You can start from arbitrary one. So this is complex geodesics, just iterates over all the faces. There's a something that does this for face on an edge. Geodesic flow or something. Is it kind of boring? Now you need to iterate it, right? Okay, let's do nest list. This is our G. So this is like, and let's highlight it on the highlight mesh or poly simplex. And that's how we can do. How that mesh cell label. Label the vertices. So here is starting from 1 to, I guess this one. Why is it? 12.
Did it extend it on both directions? Where's vertex 1? I see vertex 2.
Yeah, I'm confused too.
One question, why do you call it geodesic flow?
What the hell is happening?
Oh,
Maybe index is
vertex
not
1 and 2 are not connected.
I think the indices are incorrect or something. Or maybe some sort. Or maybe not, I don't know. It's kind of weird looking.
There's one.
It's because we provided like a wrong.
Ah,
It's kind of interesting
Do
that you can
one is
start.
connected to 7 in this.
Yeah, let's do 10 to like this. Maybe it's less confusing. Right, so if you make one more step, I guess it's gonna close. Oops.
ah,
Right.
because it's steps. Okay, now I understand.
Can you decrease the step count? Just
I think it
sanity
repeats.
check, just like decrease.
Yeah.
Make it like 4 or
I'll
something.
decrease.
Oh.
Yep. And you can start. I wonder if you start with the vertex, it's gonna stay. I guess it's not moving. Oh, it actually jumps. The highlighting is broken. This should be point. Simplex over point is not highlighted. Why it tries to go to 2? It's like the antipode. It's a bit weird. Why it jumps to an antipode?
What does? What you're starting at?
Oh, if
just
you
a
start
point?
from vertex 1,
There's nowhere to go.
if you applied it, it goes to 2.
Oh, I see. They're antipodes.
Let's do something like 59. No, it I don't know why it keeps iterating between those. Weird. So no matter which vertex you start from, it jumps to 1, 2. Well, 21, 56. Just gonna like, well, let's try some different surface. Oh, it's not necessarily like a great circle. Sometimes it does some weird thing. Interesting.
And what is like this the starting condition? What is defining the initial vector? Like the initial vector is like the oriented edge, right? And
I
what
don't
is
think
it?
in a way, yes. Yeah, you just provide a simplex as your initial condition. And then there's this geodesic flow function, which is again some weird definition. The simplex mirror, something has some weird definition that I don't also involves the stars. Though it's like depends on some ordering or something.
So is it something would we understand kind of theoretically, or how, what it actually means? Why is it? Or do you have any idea kind of why this could draw such pictures as it is drawing?
That's what we should ask Oliver.
Okay.
Okay. We should invite him and ask this kind of questions. Right now, it's just like we're doing some grunt work. Not a lot of understanding going on.
Is he helping develop this code?
No, but he has like papers and blog posts that has some code in it.
I see.
In some messy form, but that's like what I'm doing is just trying to make it more readable
Mhm.
or consistent with all other definitions. Let's try some different. Let's try the cube. Geodesics on the cube. So what have we done here? So if you have to support this cube, actually we don't need it. Let's just start with some. We did here. Just do some label. Do highlighting. G is now smash complex. It's a lot of simplicities in there, but let's start with some corner 7, 12, 7. 3 steps. More. Okay. Just gonna color it. It's weird. Try with an edge instead. Okay, that goes like this.
Get something more round.
What am I doing wrong here? Well, what we can do with the cube is just, well, there's 14.3 function. How's it called? Something with the there's some new function that smooths out the surface. Surface something.
Yeah, I remember seeing that one.
Smooth mesh. Yeah, maybe smooth mesh. Let's smooth this cube. Can you make more smoothing? We apply it twice. Oh, that's weird. I wouldn't say that it smooths it out, but okay.
I think it triangulates it, then pushes the vertices to a more smoother configuration. So it doesn't subdivide it again after triangulation.
Really?
We could try the Beethoven statue.
Well, let's try Bitcoin. Okay. Thank you. No, not cube. Not cube. Kind of slow. Yeah. Yeah, the G6 flow now takes much longer. It kind of stays there. In the local region. Oh, that's fun.
The background is neck. Oh. Oh, I see.
It's fun. Yeah. Well, that's GD6 for you. We want to do some kind of particle, like a. Do I have some papers open? Yeah, that's by the way Oliver's code. That's how he writes it. It just includes them in the paper. So that's what I'm mostly looking at and trying to clean it up
I see.
a bit.
Oh, that's really cool.
It has some examples of GD6 too here. This is basically like some disk. He also has some interacting GD6. Yeah, this one has some like almost like game of life kind of thing. But it's like interacting particle that scatter from each other.
Yeah, so there's like scattering happening. I wouldn't imagine that there's any sort of forces involved. These
Yeah,
aren't
here
like
you just like don't impose any like arbitrary rule. I think it's like the purely topological
Mhm.
dynamics happening. It's like this geodesic flow is purely depends on some permutation of your face. Permutation of your faces purely dictate which direction to move. Oh yeah, actually it reminded me of another thing I have. For example, for meshes I have some good definition of a Möbius mesh. Well, how to use it? 10 by 3. Okay. This is like a Möbius strip. So we can do some topology on that. But I also had some weird definitions. For example, highlight cell orientations. So if this is your Möbius, it has some arbitrary orientations. This is like highlighting basically depends on the particular order of vertices that it's encoded in, right? Right, these triangles are oriented in one way, the red triangles are oriented another way. It's like a signature of that particular ordering of vertices.
And if you look at
but
the other side of one of these triangles, so like rotate the mesh.
no, they are always the same color. Right, this is just highlights the permutation of that particular face. And I had some function that tries to make it orient them all in some way that they flip. We just make a smaller one. It's like too big. This is much more. See, it's like
Okay, I like
locally
that.
oriented.
That kind of makes sense.
Totally.
I mean, it's still true that this is a non-orientable manifold, but we're orienting each simplex in it.
Well, there is some confusion. I think it's like people like this is orientation of each face,
Yeah.
right? And in a way, you can orient it locally so that there's a notion of local orientability, I guess, that you can just connect two faces so that they just an opposite orientation, right? And you can do it even for this non-globally orientable surface. I think in this case, what it means that it's not orientable is that when you start collapsing those spaces, like make it like smaller and smaller, like it goes to 5, 4, like 3, 2. Like if it becomes this one, I think you can't really collapse it. I'm not even sure how to properly define in these terms the orientability, how the collapsing works. Can you do 2? Oh, that's too weird already. It's like the minimal, maybe a strip.
Right. So, to orient like one triangle is to sort of have an orientation on the triangle means it has something to do with the ordering of the vertices as listed. And then, so that induces like an orientation along each edge.
Yep. And there's some other triangle attached to it. It should induce an opposite orientation to an edge.
Right, so if I had something like this blue one here, going off to fourth vertex. And if this is like an opposite relative to the red one, this one is oriented oppositely. So like,
Yep.
so if I have,
And I think it's like when you have these two faces like that, oppositely oriented, you can contract them into a single one. Something like that. But if you with the Möbius strip, when you get to this point, you can no longer contract it with having this orientability anymore, something like that.
yeah, something like that. So
It's like right now you can't contract pair of incident faces into a single face and still have this iterated coloring. You can't longer reassign the orientations. Maybe that's what it means.
right, you can extend the orientation of one to its neighbor by sort of forcing it to agree on the common boundary component, and then that boundary component induces an orientation on this white triangle. So I can make this one red. I can extend the red orientation triangle by triangle outward, but depending on the topology of the thing, it might not work. Like it won't extend. So like if this one is here, that one's here, and then
Make it like green color or something, because red on red. It's not visible. Yeah, well, it would be nice to have this function that just checks based on this contraction. rule, whether your surface is orientable, and also extend it for arbitrary dimensional simplices.
Now we connect this one. So this orientation applied to this mesh would go the other way, which is opposite of this one. So it doesn't work right here. Yeah. Something like that.
When we have this like, where is the, I think this one is their own. No, you already removed it.
Oh, sorry.
But yeah, whatever. I think you had like this inducing in the same direction. Anyway.
Mhm. All right, cool.
So I guess what's maybe we should just talk about some plans. So what we are gonna do next? Maybe Pavel has a bunch of ideas about that. Like simply show object as a standalone citizen, that it's like more general than just list of lists, things like that.
I think one of the key points is also kind of understanding the definitions more. So reading Oliver Nill's papers maybe and have a look, actually understand what is behind. Then I mean one can also, of course, one can try to associate to a hypergraph this simplicial set or something and define some object, make a Paclet which basically represents a simplicial set with degeneracy, with face maps and degeneracy maps, and check when it's a delta complex, checks when it's when it's a simplicial complex, maybe do some kind of barycentric subdivision and so on to see how a delta complex is turned into simplicial complex and so on. So this one can definitely do like properly so that the Paclet supports these various versions of complexes. Yeah. Then what I'm actually also trying to do is because there is this notion of this, there is the notion. Actually, this you actually did not show yet, Nick. There are the notions of these propagators.
Oh
The
yeah,
green
yeah,
functions
like,
and so on.
the thing we showed like with matrices,
Yes.
for example, like Laplacians and Dirac. For example, the idea, it's one of the summer school projects this summer, for example, was basically like we have this, for example, space-time. It's just the space-time graph. No, the space-time graph. Is it like 2010? Yeah. So, for example, it's like if you want to describe some kind of, if this is your discretized two-dimensional Minkowski space-time, right? And you want to do some sort of propagator, maybe a solution to a Dirac equation, and we want to build that. We want to build it from these notions of the matrices here, right? So, for example, you can like put some particle in here, facing in this direction, and it just made it propagate like a wave. And basically mimicking the Feynman checkerboard model when the particle is just bouncing around in this lattice based on which mass it has proportional to this probability of bouncing, right? But here we want to extend this notion to arbitrary graphs, not just this simple space-time graph, because that would be like classical checkerboard. But we want like do some maybe torus, make it like do some basically close it so that it's now a torus, so it goes from left to right like a Pac-Man in space-time, and also do this propagation and prove some things about it, whether it's like an actual solution to the Dirac equation, I think, or I don't know. But this is like another completely other direction that we should take. I understand how particle propagation work on this model, on graphs and simplices.
What I would like to see on a graph like this is time-like geodesic. I think that graph is made only of basically light-like edges, right? But then
Yes.
can you make a time-like geodesic on this?
Let me actually open that summer school project and show you some pictures. Where is it? I have it. Maybe. Oh, I have it here. Yeah. So that's a Gary Low's. We were trying to generalize this model of Feynman checkerboards. Here it's like looks like a cellular automaton, but you can pretend that it's actually doing this evolution because cellular automaton is like evolution of this graph, right? So we can try to understand cellular automaton are various on different types of graphs. And here, yeah, there is a lot of math relating Dirac equation and diffusion and basically random walks. Yeah, and here we try to reconstruct this Dirac propagators using this exact matrices like we have in the Paclet, like the incidence between edges and faces. For example, a Dirac matrix, for example, contains a Laplacian. This is again has this Hodge Laplacian thing. It's like block diagonal between vertices and edges and faces.
Okay.
Constructed by
who invented this checkerboard? Because I remember that Tim Maudlin claimed that he invented this kind of stuff. But where does it come from?
Feynman, I guess, who invented it, so it was a long time ago.
Okay. Okay.
Definitely. So Katz has some notion of it even before Feynman, but it wasn't about Dirac-like propagation, but more like diffusion in space-time and its relationships with some telegraph equations on a grid. So basically some physics on a discrete space.
Okay.
Right.
So the space-time graph, I get it for like, what I don't understand is the torus graph. Can you go back to that?
No, this is just weirdly rendered torus graph, an actual torus. Do we have torus? It's sort of like this, but it's directed.
Yeah. So I get that.
Right.
You can.
Well, you just connect this point, for example, to this point, and this point to this point, so you can wrap around in both
Right,
space
right. So
and
the
time.
right wraps around to the left, and
Yeah.
everything is. You can make a cylinder that way. That is for a circular universe and time flowing upwards. But if you make it a torus graph, then you're hooking the future into the past.
Yeah.
So you
That's
have
weird.
like a cyclic
Why not?
timeline.
Yeah, maybe physically it's kind of weird, but the point is that we want to generalize Feynman checkerboard and Dirac on a discrete on discrete spaces to arbitrary graphs and complexes, how it looks like. See?
Yes, and for this we are having this green kernel, right, which is representing the propagation.
Oh, it's here in yeah. Now this connection green function matrix is again defined using this open sets. The only thing that lacks to reproduce this one in just from this purely topological notions is like the direction, because you don't know because in order to actually make the Dirac propagator as a solution to the Dirac equation, you need to know which one is how the right edge here connects to the next right edge, because locally you don't know whether you're turning left or right. So so in a way it's some global property that you have to compute or provide it explicitly to make a proper Dirac propagators.
This is actually something. It might be. It would be cool if I could relate it actually to my kind of previous academic work, where I was basically taking this Hodge propagator. I was calling it Hodge propagator. It's probably it's probably very much related to this Dirac operator. Maybe it's even the Dirac propagator. Maybe it's even the same thing. And there basically I was constructing this thing for manifolds, and I was taking like ribbon graphs. These are graphs where you at every vertex where you specify also the cyclic ordering of the edges. So basically, if you translate this information, it means that if you come from one direction, it tells you how to get out. Yeah. So for each edge, it tells you if you come here, what's the next edge to get out. And basically, for a graph with this information, I was adding like I was decorating here the propagators on the edges and with like harmonic forms on the vertices, and I was computing numbers from this and these numbers were building up some algebraic structure, and this is related actually to like the loop space, like to topological string theory. So it would be actually interesting if I could do this discretely. So if I could kind of and maybe if these graphs, which basically you compute as integrals, so here you would just somehow sum up something, and if you could these numbers which you are getting, if they would be also could be kind of modeled by this Volk or something like this. Yeah, if one could either compute it as integral or one could somehow obtain it by summing over these all possible Volks. That would be actually very much enlightening even for me what it actually means and what are the relations. So for me, kind of also I'm trying to somehow compute this propagator and try to maybe set it up and mathematically kind of relate it to what we are doing here.
Yep.
Yeah.
Would be cool. A lot to figure out.
Yeah. And there is also like concrete programming tasks. I mean, there one can also define cup product, right? On the
What is the cup product, by the way? You mentioned it multiple times.
Yeah,
Still
so
didn't get it.
basically cup product is that you take basically all possible decompositions of, it's a dual of kind of taking all possible decompositions of a simplex. So basically, I mean, yeah, one needs to actually think how to define it in this sense. It's a standard notion of algebraic topology. I think you would kind of tend to define it on a delta complex when you are having yeah. So this is, but it's definitely something one can do here. Yeah. So this
Yeah,
this
This would go
and
into like extending this all the possible operations and products on
yeah.
our objects. Yeah.
If one had this Hodge propagator, one can even think of some infinity structure actually, some kind of like do basically all this Hodge theory and kind of like this homotopy transfer of the cup product to like harmonic forms on the graph. One could kind of try to do all this stuff, like generating some other higher order products on the solutions of the forms which are in the kernel of the Laplacian. One could kind of try to really push the known geometry and structures for manifolds. One could try to push it in this framework. I mean, the fact that we are having Hodge decomposition is kind of cool. And also, we don't understand, I think, fully, or I don't understand the mathematics. I need to read also this Niels paper. We need to ask him how he came up with these formulas for the propagators, right?
Yeah. You mean like the green functions?
Yes, for the green function. This is somehow
I think it's like it's almost like I think I've heard in some videos. It's almost like computational discovery. Just he tries a bunch of stuff and just okay, like for example, the relationship that this matrix, where is it? Like this connection matrix is the inverse of this. I think it was just purely Oliver purely computationally discovered this. Like maybe he proved it or not, I don't know. But he first, by trying it out, found out that that's the case. Right? It's completely different definitions, but turns out like this uses the core, some early characteristic of the cores, and the union. Here it's like the stars with some weights, but you get two matrices and they're just inverses to each other for every complex, right?
I mean,
And also and it's
into it,
inversible because it's like not unlike it's in continuous case. This is basically a construction of the inverse, and that's what you need to solve like differential equations on our discrete
yes.
surface on discrete things. You don't have to actually invert something that is singular. You can just construct it directly. So you know the definition.
Yeah. But it is a nice illustration with this because it's precisely what it should mean, because this green functions, they are normally kind of distributions concentrated at the diagonal. So kind of outside of the diagonal they are zero, and this is precisely kind of this formula is kind of is having the same property, that you are basically just, it's non-zero just for points whose neighborhoods are intersecting. So somehow it's like propagating from one to another. It's just only it's in a way it has the correct property, but I don't understand how is it related to the inverse. Actually, it would be cool to understand if it is really this stuff, if one propagates some form on the graph using this propagator, if one will obtain solution of the equation, right?
Right. Yeah. So I don't know.
Then maybe one could think also of some notion of dual complex. This we are also not having, right?
Yeah, you could do a
We
combinatorial
have
dual.
but we defined it yesterday, like some complex dual.
How do you compute complex dual?
You can look at this is a single triangle. So the dual of triangle is this three triangles. So we can well, it's a bit confusing. For example, if you are complex dual of the tetrahedron is like some weird complex, which has 7-dimensional simplices in it. So I don't know. It's like maybe our definition is weird.
That is very strange.
So I mean,
yeah.
So I mean, dual should be something. Basically, you have some complex, right? You can view it as a subcomplex of the full complex, like of the full complex which you build on the underlying vertices, and then a dual of a simplex should be somehow complement of the simplex in this big big complex where you are embedding it in. So the dual complex of a subcomplex should be somehow the union of the complements of the simplices. Anyway, somehow this is how I would see.
I would define like very simple dual myself, like something like this is like some definition from the paper. So I don't understand it. I just defined it and I don't understand it. Right? But if I would define it myself, I would just, yes, if this is the complex and I want to dualize some simplex, as I said, yeah, I would define it like if I have simplex, all the vertices, maybe I have even vertex list, complex vertex list of G.
Yes.
Right, it's just complement of that with an X. Although it's like doesn't depend on all the other simplices in the G, but very simply something like this. Though it's not no, it's going to be the largest. You need to pick some facet. Yeah, maybe that's what confusing is. You need to pick the largest simplex of dimension of the complex that has this particular in this star. Maybe we need to simplex.
Wait, I was kind of content with the definition which you wrote down.
So that's like the older. Maybe it's just dimension is this complex dimension. And just when is this? I don't remember whether this kind of thing works. No, I don't have it. So I need to select. It's not just a select. Right, and then the complement. some kind of complement of that with an X.
Wait, so this is some kind of, you are trying to come up with some nils-like definition?
I don't know. Now I'm pretty much
Mhm.
confused how to make a good definition of dual.
I think the original one which you kind of wrote was what I would be doing.
Right now it's pretty simple. It's like
But you are right, it's kind of, it's not.
I mean,
it's like
I don't
basically
understand why
this.
the tetrahedron spit out like a dual with 7-dimensional simplices in it. Like usually a
is for
dual
me
means
also-
like you have a 1-to-1 correspondence between these simplices and these simplices, and then the dimensionality is reversed.
Yeah.
And then it's just a matter of like how they're connected. But this is interesting.
Maybe one can kind of think of a dual within the existing complex, right? I mean, you would like to, what I was describing, or what was the first implementation, there was this complement in the vertex list. This might not lie in the original simplex, but maybe one could think kind of more geometric of some dual cell actually which lies in the original simplex. This is maybe what you were trying to do, Nick, right? With this or not? With the second definition. Ah.
Maybe. So
Wait,
still need to
can
look
you show what was? Can you show what was the original definition of the dual?
Original is this. Okay.
What is that doing?
That, for example, would, for example, for the tetrahedron, it would take like this tetrahedron, look at its sphere around it, which is gonna be, right. This is like basically everything, every other simplex rather than itself, and find some intersection. But you pretend that each of those it's a new vertex. That's why there are a lot of them, something like that. You need to map it.
This definition is for me still kind of like.
I think you need to map it over vertex, right? So it's for 1, 2, 3, 4. So that's what it's doing here. So for each vertex in the tetrahedron, you computed sphere. So this is the sphere for the vertex number 1, number 2, number 3. And then it takes the intersection of those. For each. Wait.
Isn't there this one at missing?
No, I just tried it. Why is this empty? Confused. Oh, it's for the whole dual. It's computing like it's not the dual for a simple simplex, it's like the dual for the whole complex. Right? It makes a dual. Maybe it's like needs some filtering or something. It's not like we're defining as.
I don't know. I mean, does this work for a triangular graph to spit out a hexagonal grid graph, essentially? Like that would be a test for this dual function. If it's doing the same thing as like a geometric dual for that lattice.
Yeah, okay, let's try it. I kind of doubt it because it's like I don't trust the definition. Because it was a typo even in the paper about it. So I don't have trust in it. So this is our grid graphing. So on this one that you want to write, right? So that it returns a hex of sorts. Let's make it. I haven't defined. Let's make it smaller. Slow. I think it's a no. It's not gonna work. Even for this one, it's. Oh, I'm trying to render it. I'm trying to render it. Try to make measure complex curves. Maybe face curve. Is it sensible? I haven't made the actual blue. Oh my god. Eh. Oh, there's some empty lists in there. And if you close it, it's kind of horrible. Yeah, it's a bad definition. We need to figure out the proper one.
Mhm. And also, what is the meaning of this Nils definition actually? This intersection of spheres.
It was very confusing. Was it in this paper? Good already.
Dual graph there.
I had some definition with the intersection. Maybe
Another thing, what came to my mind, what we can also do, it would be nice geometry, because this torsion is used to distinguish, for instance, length spaces, right? And maybe do we have some discretization of some of such objects?
of space.
Length spaces. I think this torsion is an invariant which was used to distinguish length spaces. If I'm not mistaken, it's a long time since I was looking at it.
Yeah,
And
so
they
like
are
I'm
having
familiar
a-
with torsion for like a curve
Yeah.
embedded in 3 space, and it has had like a helical motion to it or something like that. Is there a notion for torsion for like manifolds?
No, it's a different notion of torsion. It's a notion of a torsion for a chain complex.
Okay.
There is basically the most famous theorem about it is Cheeger-Miller theorem. There is a Milnor's algebraic notion of torsion and analytic notion of torsion. Actually, torsion is something which you also obtain when you are computing like free energy of Chern-Simons theory, like the z, the partition function, and as a coefficient you obtain actually torsion.
Mhm.
And this is some kind of like super determinant of the Laplacian. So basically, you take the Laplace blocks in different
Yeah.
dimensions, and you compute a super determinant of that. And it can also be computed on the chain. There are various ways how one can compute it. One can check that yes, it's here. Yes. Yes, so it's like the superdeterminant also of this Dirac operator. Yes, and it's also related. It's also related to this It's the same thing as superdeterminant of this LK, right? If you scroll up, maybe a bit, or square root of how does he have this formula? Yes, here upstairs. yes, superdeterminant of L, and it should be equal.
I think it's just up to square root something.
Yes,
Yeah.
square. Yes, square root of the superdeterminant of the Laplacian. This should be.
Like this something.
Yes. And basically it's a well-known theorem, like Milnor or somebody used it too, because length spaces are some quotients of the two-sphere, three-sphere. I'm not sure anymore, and they are having like the same homology, all of them.
Yeah, it's a
And-
three sphere with like certain segments of the
Yeah.
boundary
Yes.
glued to each other.
Yes, and they are having probably the same homology, the same maybe cup product, maybe they are the same as algebras. And actually, how you kind of distinguish them is by computing distortion. It would be cool if we could have some maybe discrete model. I'm not sure if people are having discrete model of length spaces, and somehow.
Well, you can model it as a CW complex, I think.
Yeah.
And so, yeah, it'd be interesting to have a discrete version of that. I think that's
Yeah.
what delta sets are sort of doing, is like you have a simple complex, but you
Yes.
also have mappings
Yes.
on the boundary elements to each
Yes.
other to sort of have a gluing
Yes.
or quotient space.
Yeah. So
I think
So I think
delta
the
set is basically the Dirac matrix, right? You just define it by arbitrary Dirac matrix. It's like one
Yes.
of the data.
No, yeah, so I would study actually for this length spaces. One could maybe have a look at the definition. One could maybe see like mathematically, maybe easily, what's the corresponding delta complex, and then one could take this delta complex. One can take double subdivision of it, because double barycentric subdivision of a delta complex is going to give you Simplish complex. Because in delta complex you can have kind of like these multisets, and you kind of get rid of the multisets by adding some points in the middles of this. I mean, during this barycentric subdivision, and then one can compute distortion for it, and one could see how it comes. This would be actually cool. This would be yeah, because I never actually saw the computation, the standard, how people do it in differential geometry. If we can do it for the representing complex. But I mean, it's a probably a standard thing. It's not like direction hypergraph rewriting. This hypergraph rewriting would be another direction, right? We should kind of take hypergraph rewriting as some kind of, we should view it as what we were discussing yesterday. We should view it as matrices, basically between the Simplish complexes, and maybe study what properties are going to be. Let's study hypergraph rewriting rules which are going to be compatible with Dirac operator or something like this, and which are going to kind of like commute with Dirac operator, or yeah. So we should actually go in the direction of hypergraph rewriting and maybe study some stable properties which are going to be stable under it.
Yeah. But the plan is basically formulate the usual rewriting as the same kind of propagators that we're talking about with matrices. Make it linear algebraic in nature. Some kind of constraint, and all the ambiguities of rewriting is basically encoded in the matrix so that it tells you how the field evolves instead of multiple hypergraphs that one can produce with a single rewriting rule.
I
It's
mean,
like
you are
naturally superimposed on each other, something like that.
you are talking like representing the hypergraph rewriting rule on like a sum of the matrices of each of the possible applications.
Yeah, we were planning like enumerate all the possible hypergraphs that can be an input to a given hypergraph rule, right? For each of those, you just create a matrix by like just like all the possible simplicities of the maximal dimension of that left-hand side rule and right-hand side rule, right? Just and sum them over, and that's your like that's the matrix that describes hypergraph rewriting rule, that particular rule for all possible cases, and then just apply it, and you basically get some superposition instead.
Yes.
Right. Though it's like not decomposable into original hypergraph, but more like a field now. Something like that.
Yes. At least then, if we had rewriting rules yeah, we could take actually superposition of that. We could take arbitrary coefficients. Somehow we could play even with that, right? Somehow we can sum the matrices with coefficients and I don't know.
All right. I
Could
think
be
we should
interesting with
wrap
some
up.
negative. Go ahead.
I was just saying maybe we should wrap up. And
Yeah, well, yeah, I think so.
pick this up some other time. It's a good discussion. Really good work. I look forward to looking at future progress. All right. Thanks for everyone tuning in on Livestream. See you again next time.
That was great. Thanks, guys.